Hey everybody, and welcome to Pandas Challenge number 2. Explain the 1000 times speed difference when taking the mean. As usual, all challenges are available on the Dunder Data GitHub repo and at the Medium Dunder Data blog. Alright, so I'm going to show you, this challenge is going to compare the difference between taking the mean on a data frame with just the defaults, the mean method, versus using this parameter numeric only equals true. So the results will be the exact same, but the speed difference will be extremely pronounced. So we're going to use this bikes data frame, which contains data from the city of Chicago. It actually has 50,000 rows, but just so that the time doesn't take forever, because there's a 1,000 times speed difference, and I don't want to sit here for an entire minute waiting for it to compute, I'm just going to read in the first 10,000 rows. So it's going to make it much easier to compute while I'm working in a video. So here are the first 3 rows. It's just every row is a ride in the city of Chicago in the year 2013, a bike ride in the public bike system they have there. All right, so yes, it's good to find the shape. So there's 10,000 rows and 19 columns, and you can see there's some that have strings or date times, for instance, or whatever. Lots of numeric columns. All right, so whenever you take the mean of a data frame, whenever you call the mean method on a data frame, what it does is it goes through column by column and it attempts to compute the mean of that column. So if a column does not have a mean, then it just will skip it. It's considered a nuisance column and it is thrown out of the result. So you can call the mean method on all of the data, even though strings clearly do not have a mean. So let's go ahead and run this. You can see that it is taking a little bit of time there. So I don't know if you saw that. Let me run it again. So if you see the star over here, it's taking a little bit of time to compute. And you can see that there's definitely less than 19 columns that are returned. These are all the numeric columns, and this is just the mean of them. So the data is not, we're not caring about the data. We're caring about the speed difference. All right, now you can use the same method, but use the numeric only option equals true. So it's the same exact method, but I'm just going to set this option to true, and you should see a pronounced difference. So that happens instantly. So let me run it again. So it is the exact same result. So if you notice here, you'll see that it is the exact same result that is displayed, just the mean of every single column. Okay, so why does using numeric only equals true make such a dramatic difference in time? Now, it's not 1,000 times difference, which you may be wondering, but if you did it on the full data set of 50,000 rows, it will be actually more than 1,000 times difference. So, yeah, the result is the same, but the time is astronomically more. All right, so let's go down here and actually we'll time this operation. This just does it one time. That's all it's saying. So I just timed each one. If I did it, so time it as a magic command that simply just times it, and you can tell it like how many runs of each one. So you could do like 5 runs of 10 or whatever. So this is N and R, the options that control that. So this just said, I just did it one time since I'm running it live for a video. We get, it took 3 seconds for the defaults and only 8 milliseconds. That's milliseconds, which is 1/1000th of a second. So actually it's still quite a lot. That's about a 400 times difference. So a second is 1,000 times a millisecond. So it's still actually quite a bit more. Not quite 1,000 in this example, but if you had more data, it would be it actually increases exponentially. So a very massive difference there. All right, so let's that's the setup to the problem. So if you want to try it, you can stop the video here and see if you can figure it out. I'm looking for an explanation why there's such a massive difference in time. All right, so continuing. So I'm going to back up a step and just create a simple series with integers here. Now, I'm just called sint. So, pandas, of course, you can take the sum of this with the sum method, and you can take the mean. So this is just a series, so just is like one column of data, so you're just getting a scalar value in return. Now, you can change data types. So this is formally an integer object, but I'm going to change it to, I'm going to change the data type of the values in the series to object. I'm going to call it s underscore obj. And if we look at this, the data will look exactly the same, but it is in fact a object data type. And I'll go a little bit more into this later. But if you go ahead and compute, like say the sum and the mean, it'll still work just fine. So I'll get 74, and then the mean will be computed the exact same. So on the surface, if you're unfamiliar with pandas, it looks like everything is happening the same. Like it doesn't matter that this is so this is formerly an int64 data type, and this is now an object data type. So on the surface, they look the same. The output is the exact same, but the computations are the exact same, but the data type is different. All right. So one thing that is different, and I need to have another one up here, is that so the way the data is stored is very crucial in pandas. The difference between these are stored is very, very different. So what happens here is pandas actually stores this data in a NumPy array, and NumPy arrays store their data as C arrays in contiguous memory, and this gives it a highly optimized performance. Now, when you change it to object, this is a drastic change to the actually individual values in your series. So they're no longer C integers. They're now sometimes it's called fully fledged Python integer objects. So Python integer object is a much bulkier object. It's wrapped in it has its own methods and its own attributes, and it's an actual Python object. So you're no longer working like directly with C and contiguously allocated memory. You're on the Python service, so it's the operations become much slower. So you would never want to actually change an integer series into an object series. It just doesn't make any sense. So just to prove it to you that they are different. So yes, I'm just going to look at one of the actual values of this of this series, and let me just move that out of the way. So if I look at the very first value in my sint series, it looks like it's 10. But if I look at the actual type of this, it says it's it's still in NumPy, okay? It's N64. And if I look at the object series over here, and I look at the very first value, lo and behold, actually this is a Python integer, okay? So when I did this as type object, I'm now in this bulkier Python integer and not a nice optimized C integer as it's stored in NumPy. Okay, so operations on an object array are slow, and I'm going to prove it to you here. So I'm going to dip down into NumPy for a little bit to show you how these operations are quite slow with it. So I'm going to create an array of 1 million integers from 0 to 10. So I'm going to store that as a int, and then I'm going to have a underscore obj, which is the same exact integer array, same 1 million numbers, but they are now Python objects. So if you look at them, again, they look the same on the surface. And NumPy actually outputs the data type here for the second one, so I have an object. Here it is actually an int 64. All right, so here I'm going to sum them up. Again, I'm going to sum up both of them just so you can see the difference. And I'm going to time them. Here I'm actually doing five loops, and it just chooses the number of runs. So when I'm summing up the integer array with an integer data type, a underscore int, it takes 1 millisecond versus 39 milliseconds for the object. So, I'm recording, so there's a lot of resources running right now, and so you'll get different times, of course. But this is there's still about a 40 times difference between, the C integer versus the Python integer summing it up. So it's a dramatic difference when you convert to object. Okay. So stepping aside from that real quick, so we're going to get back to the challenge here. Almost back to the challenge, I should say. So if I look at, so strings in Python, so just regular Python strings. So say I have one string that's equal to Mac and another string that's equal to Hein, and then I add them together, I get machine. So the plus operator in Python concatenates strings together. So it's a very easy way to concatenate. So the plus sign works with strings. So this creates some interesting things. So I'm going to create now a series with nothing but strings in it, just a simple series so we can kind of walk through this. So I just have, 4 words, the quick brown fox. So this is an object series. So when you create a series or a column of data in a pandas data frame with strings in it, pandas must use the object data type. So there is no specific string data type for pandas, or well, there is one for NumPy, but there is no one for pandas. So and object data types can contain any Python data in it. Any data type in Python can go into an object data type. So these are what I call infinitely flexible. They can take anything in there. The values, you could have strings mixed with numbers, mixed with even series or lists or dictionaries or whatever you want can fit into a pandas series with the object data type. So so we can sum this series up. So here's our series, and the sum method actually does work. So it computes. So all it does is go one by one and adds them all up, and it just concatenates them all together into a single string. So that's the value of the sum. So it's a little strange and a little bizarre that this actually works, but it does compute. Now, if you take the mean of this series, so this is the same series, s.mean, well, this is not going to work because the mean doesn't make any sense when you think about strings. There's no average value of a string. So if you look at the error message is actually very telling and is what's going to sort of reveal what the issue is. It says, could not convert the quick brown fox to numeric. So it looks like pandas has actually already done the sum. So the mean is simply the sum divided by the number of values, divided by n. So it's already concatenated everything. So it basically just called sum, and then it tried to divide by n, and that's when the error happened. So it already went through the trouble of concatenating everything together. So it didn't skip that step, and it becomes more pronounced if you have a lot more data. So let me just multiply this by like 1,000. So say there's 4,000 values in here. So if I sum this up, it's a large value. And let me just comment this out real quick. So if I take the mean, you'll see that, okay, so you can definitely tell here, it actually shows you the sum of the whole string first in the error message. So this should verify to you that everything in the string is summed up, concatenated together first, and then the error, occurs. So I can get rid of that and go back to just this. Okay, so this is the main thing. Could not convert the quick brown fox to numeric. All right, so one little note here is so why is there no error when I sum up the bikes data frame? So if I look at the bikes data frame, it completes normally when I take the mean, right? Or the sum, excuse me. So why is there no error here, or the mean? If I take the mean here, it takes a few seconds. There's no error, even though it has these string columns. So what pandas does, it treats series and data frames differently. In that if you have a column in a data frame where the sum or the mean or whatever is not able to be computed, it will simply treat it as a nuisance column and then ignore it. It'll drop it from the result. So what pandas does is it actually tries to compute the mean on every single column, and if it fails, then it will just skip it and move on to the next column. So I can prove this to you. So here, on a series it doesn't work that way. So you take the mean and you get an error like we just saw above. But if you convert this series to a data frame, and there's a toFrame method, and you can actually you can say what you want the one column to be. Okay, so here's my data frame. Let's call it df. Okay. Now, if I take df.mean, well, it's a data frame, so this is actually going to compute. So there's no error. It's just simply return nothing. There's no columns in the data frame where the mean works. It's a one-column data frame. It has the same exact values as the series, as s, but s.mean gives me an error, and now df.mean does not, because pandas will throw away the nuisance column. So that's a one difference between a series and a data frame. All right, so just so we have a full explanation here as to why it's taking, what the speed difference is doing. So when pandas takes the mean, All right, so it does the sum first, and the sum is a valid computation for string columns. So it's going through every single value, and I can just remove this. It's going through every single column, it's summing it up first, and then it's dividing by n. So it's doing all this concatenation, this pointless concatenation of strings, column by column by column, and that's a very, very expensive operation. So a string concatenation is very expensive, and as the string gets longer, it's even more expensive. So you can see how a string of or a data frame of 50,000 rows can get exponentially, more. The performance can be hit exponentially more. So that's what Pandas is doing when you do with the default. It tries to compute the mean. It'll concatenate all those rows up. Then it'll divide by n. It'll figure out, oh, I can't divide a string by n. And it'll then move on to the next column. So the reason it does this is that it doesn't make any assumptions on your data in the object column. So since objects are infinitely flexible, you can have an object column that's nothing but integers. So if you have a column that's nothing but integers, it can still take the mean of that object column, as we saw in the very beginning of this video. All right, so that's what's happening. It's taking many seconds or whatever. It's taking a lot of time to do user type or gender or whatever the strings are, and then it fails, and then it removes it as a nuisance column. So when you do numeric, numeric only, and you set this equal to true, so by default it's false, then it only looks at the numeric column, which are the integer and float columns, and it just automatically skips the string columns, so it doesn't have to, it doesn't go through that whole trouble of trying to figure it out. So this can save quite a bit of performance time, if you're unaware of that. So if you're getting the right result, but you're getting terrible performance when taking the mean, you might need to use this numeric only parameter. All right, so a couple of questions here. So why can't Pandas just skip columns of strings? Well, it could do that. It would have to inspect every value in an object column, and if it's a string, then it could skip it. So it's just not built that way. And then the other thing is, well, why can't so Pandas could build a special case for this. The other thing is that so the real unfortunate thing here is that there's no string data type in Pandas, and this causes unfortunate errors like this, or performance issues like this, or even errors when people put together strings and numbers and all sorts of data type in the same exact column. So it would be much nicer if there was a data type, that was just for strings in Pandas, and you could be guaranteed to only have strings in there. But unfortunately, that's just not the issue. So we have to deal with little idiosyncrasies like this. All right, so I hope you enjoyed that challenge, and there'll be several more coming up, and so yeah, just I hope you enjoyed it, and yeah, I'll see you in the next challenge.